This is extra material for the OLLI course. Planck's constant. Planck's constant H is present in the equations of quantum mechanics, in the Schrödinger equation, and in all quantum mechanical results: energies, time variation, size of atoms, bonding, angular momentum, results that have no obvious relation to a black body cavity. Planck's constant is a universal physical constant. Let's first look at its dimensions or units, then we'll look at its value. The dimensions of H are energy times time. This is not a quantity that is familiar to us. Physicists call it action. But when we multiply by frequency of light, 1 over time, we get the energy of the photon. Let's get the dimensions of energy from kinetic energy. Kinetic energy is 1/2 mass times velocity squared. The 1/2 is just a number, it has no units, so the units of energy are mass times velocity times velocity. And the units of Planck's constant are energy times time, so mass times velocity times velocity times time. We can group this as mass times velocity times velocity times time. If you know a little physics, think about this and see if you can express these differently. Mass times velocity is momentum. Velocity times time is distance. So we started out with that the dimensions of Planck's constant are energy times time, but those are the same dimensions of momentum times distance, and that is also the same dimensions as angular momentum. Planck's constant plays a central role in the angular momentum of electrons in atoms, as will be determined in 1913 and 1926, in Heisenberg's uncertainty principle in 1927, that there is a limit to how precisely we can simultaneously know the position and momentum of a particle such as an electron. This is completely different than classical mechanics. And also wave-particle duality in 1924, which is also completely different than classical mechanics. Now, let's look at the value of Planck's constant. Planck's constant H has dimensions of energy times time. Physicists always use seconds as the unit of time. And for large things, macroscopic things, the energy unit is joules. Well, how much is a joule? This is a 2-pound weight, little less than a kilogram. If I move it up this high, it took me 1 joule of energy to move it that high. If I do it in 1 second, that's 1 watt of power. 1 watt of power. So that's a joule. It's a reasonable macroscopic unit, but it's way too big for dealing with electrons and atoms. Physicists use, and so the value of Planck's constant is 6.6 times 10 to the minus 34 joule seconds. Now you look at 10 to the minus 34 and say, oh man, it's really small constant. That's cheating a little bit because we don't really know if that's big or small. But probably the unit of joule is too big a unit for electrons and atoms. Physicists also use the energy unit, an electron volt. So the joule is a practical energy value for our macroscopic world, but it is way too large, 19 orders of magnitude too large for the energies of electrons in atoms and also for visible light photons. The electron volt, which is shortened to EV, lowercase e, capital V, is the practical energy scale for atoms and photons. 1 electron volt is the energy that will be imparted to an electron that travels across 1 volt of potential energy. But what's 1 volt? Well, a car battery is 12 volts and house current is 110 volts. So that gives you some idea of a volt, and your ability to understand an electron volt will improve over time as you get more experience. So I can't magically make it make sense to you. But an electron volt is a much smaller unit than a joule, so Planck's constant in electron volt seconds is 4 by 10 to the minus 15 electron volt seconds. Now, you might say, well, 10 to the minus 15, that also seems low, but actually the frequency of visible light is pretty high, and so in fact this will turn out to be a good-sized unit. Now, quantum mechanics also defines a variable, a constant called the reduced Planck's constant, which is this symbol, which is called h bar, and it's h over 2 pi. It just happens that that's a very useful quantity in all of quantum mechanics, and so it has these values, and it's also useful to multiply Planck's constant by the speed of light, and then we get a constant whose dimensions are energy times distance. That is also useful. You don't need these for this OLLI course, however. Visible light wavelengths are 400 nanometers for violet to 700 nanometers for red, where nanometers is 10 to the minus 9th meters, a billionth of a meter. We can calculate the photon energy for a particular wavelength as hc over lambda, which is why hc is a useful constant to have pre-computed. So in the table above, hc was 1.24 by 10 to the minus 6th electron volt meters, and if we divide that by wavelength lambda, we will get the energy of a photon in electron volts. If we calculate the energy for 400 nanometers, which the denominator here, 400 times 10 to the minus 9th meters, we would get 5 by 10 to the minus 19th joules, or 3.1 electron volts. The fact that a violet photon has a small number, 3 electron volts of energy, makes the electron volt a useful energy scale for visible light. It also turns out to be a really useful energy scale for electrons in atoms. A 400 nanometer violet photon has 3.1 electron volts of energy per photon. A 700 nanometer red photon is 1.77 electron volts. So you're not really familiar with electron volts, but maybe you can get used to remembering that visible light photons have energies in the range 2 to 3 electron volts. So that might be the best we can do for the moment for getting used to the energy scale. Now, infrared photons have less energy than visible light. A 1 micron wavelength infrared photon has 1.24 electron volts. Infrared photons have less than 1.77 electron volts. Ultraviolet photons have more energy than violet, so more than 3.1 electron volts. Photon energies span 27 orders of magnitude, from 10 to the minus 14 electron volt radio waves to 10 to the plus 13 electron volt gamma rays. Books say that Planck's constant is small, and that's why quantum mechanics applies to things that are small, like atoms. But small is a relative term, which is to say it's also kind of a useless term. Unless you know the scale you're talking about, we should not say that something is small without having a reference scale to compare. So you need to see different results to get a feel for smallness. The smallness of Planck's constant separates the quantum world from the classical macroscopic world. But the size of Planck's constant gives the atom its size. So the smallness of Planck's constant is just right to give us our universe and life. So it's small, but it's just right for the size of atoms in our universe. How well do we know Planck's constant? We know it to 9 significant figure precision. Only one other physical constant is known to higher precision. Planck's constant has the same experimental value for photons, electrons, and neutrons. Planck's constant is the same on Earth as the Sun and other stars and other galaxies. Planck's constant is the same here and now as 12 billion years ago, 12 billion light years away. So Planck's constant is a universal physical constant. Now you might step back and ask yourself, how can physicists possibly know that Planck's constant is the same here as in faraway galaxies? And how can they know that it's the same now as 12 billion years ago? That would be a good question that you should ask yourself and see if you can figure out the answer. The magnetic moment of the electron is a property. We're not going to discuss the property in this course, but it's a property that can be experimentally measured, and it can be calculated from quantum electrodynamics field theory. And the result agrees with experiments to 13 significant figures, the most successful result of any scientific theory and experiments. This is the end of the short supplement for the OLLI class.